Myself, Dr. Priyodip Das, Associate Professor Research from Department of Chemistry, SRM Institute of Science and Technology. Today we are going to discuss the topic palladium-catalyzed cross-coupling reactions with carbon-carbon bond formation. In this lecture, we will cover 4 important cross-coupling reactions with carbon-carbon bond formation. Hague cross-coupling reaction, number 2 Negishi cross-coupling reaction, number 3 Kumada cross-coupling reaction, and number 4 Suzuki cross-coupling reaction. These 4 are very important cross-coupling reactions for carbon-carbon bond formation using palladium catalyst and several organometallic reagents. In this lecture, we will discuss this reaction with detailed mechanism and synthetic applications. Role of palladium catalyst in organic reaction. Palladium is probably the most versatile and exploited transition metal in catalysis due to its capability to promote a myriad of organic transformation, both on laboratory and as well as an industrial scale. Both homogeneous and heterogeneous palladium catalyzed reaction continue to play an essential role in organic synthesis. Natural alkaloids, bioactive compound, pharmaceutical reagent, agrochemicals, especially the polymers, etc. can be effectively accessed by means of palladium catalysis. In general, palladium-based catalysts are involved in a variety of organic reactions such as alkylation, arylation, cyclization, hydrogenation, oxidation, isomerization, cross-coupling, cascade, radical reaction, etc. Particular attention is developed to the use of palladium catalyst in CH bond activation, carbonylation and asymmetric reaction, or in combination with other metals. High chemo, regio and diastereoselectivity as well as high levels of molecular sophistication can be achieved by employing the tailored palladium-based catalytic system under mild reaction conditions. However, despite this development, every day new exciting palladium-based applications are disclosed, giving renewed emphasis to palladium chemistry. Therefore, the original research papers and the reviews focusing on recent advancement in the field of palladium catalyzed transformation are welcome for inclusion in the special issue of catalysis. Basically, palladium catalyst can be employed in the following main categories. Homogeneous and heterogeneous palladium catalyst can be employed for palladium catalyzed cascade reaction, palladium catalyzed cross-coupling reaction, palladium catalyzed carbonylation reaction, and palladium catalyzed asymmetric reaction. Now we are going to study different palladium catalyzed cross-coupling reaction with carbon-carbon bond formation. First, we will going to study the Hague reaction. Hague reaction is a palladium catalyzed cross-coupling reaction between organohalide or triplet with olefin. So here is the general reaction. RH react with the activated alkene in presence of palladium 0 catalyst to produce the cross-coupling product with carbon-carbon bond formation. In the organohalide, X equal to iodide, bromide or triplet or chloride, and Z equal in the activated alkene become hydrogen, alkyl, aryl, cyanide, ester, alkoxy, acetate or amide, etc. This palladium catalyzed coupling reaction between the aryl halides or vinyl halide with the activated alkene in the presence of a base is mainly referred to as the Hague reaction. Nowadays, the recent development in the catalyst and the reaction condition have resulted in a much broader range of donors and acceptors being amendable or used in the Hague reaction. One of the major benefits of the Hague reaction is outstanding trans-selectivity. So when this activated alkene react with the aryl or vinyl halide in presence of a base or palladium 0 catalyst, the alkene produced with the new carbon-carbon bond formation is always the trans product. Let us see the history of the Hague coupling reaction. The original reaction by T. Mizoroki in 1971 described the coupling between iodobenzene and styrene in methanol to form Stille at 120 degrees centigrade. And the reaction it carried out in autoclave with potassium acetate base and palladium chloride catalyst. This work was an extension of the earlier work by Fujiwara in 1967 on the palladium-2 mediated coupling of arenes and alkenes. An earlier work by Heck in 1969 on the coupling of aryl mercuric halide with alkene using a stoichiometric amount of palladium-2 species. Later, in 1972, Heck acknowledged the Mizoroki publication and carried out the independent work and discovered that reaction condition differ in terms of the catalyst palladium acetate, and catalyst loading is 0.0 equivalent, and he used a sterically hindered amine base without any solvent. In 1974, Heck shows that the phosphine ligand can facilitate this coupling reaction. And Heck reaction, this is the Heck reaction in 1974 with phosphines. So now look into that the several examples of Heck coupling reaction. These two examples are the Heck coupling reaction between the aryl halide with alpha beta unsaturated ester. Now look into the mechanism of the Heck coupling reaction. This is the basic diagram or mechanistic diagram of the Heck coupling reaction. Involves several steps. The first step is the oxidative addition of the aryl halide to the palladium 0 species. Later is the coordination of the activated alkene into the palladium 2 species. Then the cis insertion of the alkene. And the next step is the cis beta elimination with the carbon-carbon bond formation, and finally the PDHX in the presence of base again come back into the palladium 0 species, so the catalytic cycle is going to continue. Now we will discuss the mechanism of the Heck reaction in details. The mechanism of this vinylation involves organopalladium intermediates. The required palladium 0 compound is often generated in situ from a palladium 2 precursor. For example, palladium 2 acetate is reduced by triphenyl phosphine to bis triphenyl phosphine palladium 0 species 1 with the concomitant oxidation of triphenyl phosphine to triphenyl phosphine oxide. Step A is an oxidative addition in which palladium inserts itself in the aryl bromine bond. The resulting palladium 2 complex then binds alkene 3. In step B, the alkene inserts into the palladium carbon bond in a syn addition step. Step C involves a beta hydride elimination with the formation of a new palladium alkene bicomplex 5. This complex is destroyed in the next step. The palladium 0 complex is regenerated by reductive elimination of palladium 2 compound by potassium carbonate as a base in the final step D. In the course of the reaction, the carbonate is stoichiometrically consumed and palladium is truly a catalyst and used in the catalytic amounts. A similar palladium cycle but with different sins and ester is observed in the Walker process. So now we will going to study the Negishi cross-coupling reaction. The Negishi cross-coupling reaction is a widely employed transition metal catalyzed cross-coupling reaction. The reaction couples organic halide or triplets with organo-zinc compound, forming carbon-carbon bonds in the process. A palladium 0 species is generally utilized as a metal catalyst. Though nickel is sometimes used, a variety of nickel catalysts in either nickel 0 or nickel 2 oxidation state can also be employed in the Negishi cross-coupling reaction, such as nickel triphenyl phosphine, nickel diacetyl acetone, nickel cyclooctadiene, etc. So this is the general reaction of the Negishi cross-coupling reaction when Rx, the organic halide, reacts with the R1ZnX dash, the organozinc compound, to produce the RR dash. This is the Negishi cross-coupling product with carbon-carbon bond formation. The leaving group X in the organohalide compound, usually the chloride, bromide and iodide, but triplet and acetoxyl group are also feasible. But in X equal to Cl usually leads to very slow reaction. The organic residue R in organohalide compound is usually alkynyl, aryl, allyl, alkynyl or propargyl. The halide X in the organozinc compound can be chloride, bromide or iodide. And the organic residue R1 in the organozinc compound is alkynyl, aryl, allyl, alkyl, benzyl, homoallyl or homoproporzyl. The metal M in the catalyst is either nickel or palladium. The ligand L in the catalyst can be triphenylphosphine 1,2-bis, diphenylphosphinoethane, binab, etc. Palladium catalysts in general have higher chemical yields and higher functional group tolerance in compared to the nickel catalyst. The Negishi cross-coupling find common use in the field of total synthesis as a method for selectively forming carbon-carbon bonds between complex synthetic intermediates. The reaction allows for the coupling of sp3, sp2 and sp carbon atoms, which makes it somewhat unusual among the palladium-catalyzed coupling reactions. Organozincs are moisture and air sensitive, so the Negishi coupling must be performed in an oxygen and water-free environment. A fact that has hindered its use relative to the other cross-coupling reaction that require less robust condition like Suzuki reaction. However, organozinc compounds are more reactive than both organostanins and organoborates, which correlate to the faster reaction time as well. Now, let us consider the mechanism of the Negishi coupling reaction. The reaction mechanism is thought to proceed via a standard palladium-catalyzed cross-coupling pathway. Starting with a palladium 0 species, which is oxidized to palladium 2 in an oxidative addition step involving the organohalide species. The steps proceeds with aryl, vinyl, alkynyl and acyl halide, acetate or triplet with substrate following standard oxidative addition relative rates is iodide greater than triplet, greater than bromide, greater than chloride. The actual mechanism of oxidative addition is still unresolved, though there are two likely pathways can be proposed. The first pathway is thought to be proceed via an SN2-like mechanism, which can result the product with inverted stereochemistry, and the other pathway proceeds via a concerted addition and retain the stereochemistry of the final product. Here you can see the two possible pathways. One is the concerted pathway that can give the final product with retained stereochemistry, and another one is SN2-like mechanism. We can give the final product with inverted stereochemistry. Though the addition are ceased, the palladium 2 complex rapidly isomerizes to more stable tran complex. The next step is the transmetallation step. In the transmetallation steps, where the organozinc reagent exchanges its organic substituent with the halide in the palladium 2 complex, generating the trans palladium 2 complex and the zinc halide salt. The organozinc substrate can be aryl, vinyl, allyl, benzyl, homoallyl or homopropargyl. Transmetallation is usually the rate limiting, and a complete mechanistic understanding of this step has not been yet reached, though several studies have shed light on this process. It was recently determined that alkyl zinc species must go on to form a higher order zincate species prior to transmetallation, whereas aryl zinc species do not. Studies indicate competing equilibrium exists between the cis and trans bis alkyl organopalladium complexes, but that the only productive intermediate in the cis complex. The last step in the catalytic pathway of the Negishi cross-coupling reaction is the reductive elimination, which is thought to proceed via a 3-coordinate transition state, yielding a coupled organic product and regenerating the palladium zero catalyst. For this step to occur, the aforementioned cis-alkyl organopalladium complex must be formed. So both the organozinc halide and diorganozinc compound can be used as a starting material. In one model system, it was found that in the transmetallation step, the former give the cis adduct RPD adduct, resulting in first reductive elimination to product, while the latter give the trans adduct, which has to go through a slow trans-cis isomerization first. Now we are going to study the mechanism of nickel to catalyze Negishi cross coupling reaction. Nickel catalyzed system can operate under different mechanisms depending on the coupling partners. Unlike palladium system, which involve only palladium 0 and palladium 2 oxidation state, nickel catalyzed system can involve nickel of different oxidation state like nickel 1, nickel 2, nickel 3 as shown in the catalytic cycle. Both the nickel and palladium system are similar in that way that they involve in similar eliminatory steps like oxidative addition, transmetallation and reductive elimination. Both systems can also have to address the issue of beta hydride elimination and difficult oxidative addition of alkyl electrophiles. Therefore, for unactivated alkyl electrophile, one possible mechanism is the transmetallation step will be happen first. So in this mechanism, the alkyl zinc species would first transmetallate with the nickel catalyst in the first step. Then the nickel would abstract the halide from the alkyl halide, resulting in the alkyl radical and oxidation of the nickel after addition of that radical, as shown in the catalytic cycle. One important factor when contemplating the mechanism of a nickel catalyzed cross-coupling Negishi reaction is that the reductive elimination is facile only from nickel 3 species, but very difficult from nickel 2 species. To scientists Kochi and Morel provided evidence for this. They isolated nickel 2 complexes and showed that they didn't undergo reductive elimination quickly enough to be involved in the eliminatory step. Now we will going to study the Kumada cross-coupling reaction. The Kumada cross-coupling reaction was the first nickel or palladium catalyzed cross-coupling reaction which was developed in 1972. This coupling reaction consists of Grignard reagent react with alkyl vinyl or aryl halide under palladium or nickel catalysis, which provides an economic transformation. But the reaction is limited to halide partners only that do not react with the organomagnesium compound. One example is in the industrial scale production of the styrene derivatives. And the Kumada cross-coupling reaction is the method of choice for the low-cost synthesis of unsymmetrical biaryl compounds. The main or major advantage of this reaction is the direct coupling of the Grignard reagent, which avoids the additional steps such as conversion of Grignard reagents to zinc compounds for the starting materials, as we have observed in the nickel catalyzed Negishi cross-coupling reaction. This reaction is notable for being among the first reported catalytic cross-coupling methods. Despite of the subsequent development of alternative reaction like Suzuki, Sonagashira, Stille, Miyaura, Negishi, the Kumada coupling reaction continues to be employed in many synthetic applications, including the industrial scale production of aliskirin, hypertension medication and polythiophins, useful organic electronic devices. The Humada cross-coupling reaction, which is also occasionally known as Kharas cross-coupling reaction, is basically a nickel or palladium catalyzed cross-coupling reaction of a Grignard reagent with an organic halide and triplet. The Kumada cross-coupling reaction, as well as the other cross-coupling reaction like Negishi, Stille, Miyaura, Suzuki cross-coupling reaction, belong to the same category of a palladium catalyzed cross-coupling reaction of organic halides or triplet with other electrophile and organometallic reagent. So these reactions follow basically a general or similar mechanistic cycle. Therefore, there is some slight variation in the Miyaura and Suzuki cross-coupling reaction, for which an additional activation step is required for the transformation or the transmetallization step. Here you can see the reaction, general reaction of the Kumada cross-coupling reaction, where the RH, the organic halide, react with R1 FGX, the Grignard reagent, in presence of palladium 0 catalyst to produce the cross-coupling product with the formation of MgX2. So here we can see the mechanistic cycle of this Kumada cross-coupling reaction. In the first step is the oxidative addition of palladium 0 with the organic halide. Next step, the transmetallization step or transmetallization isomerization in presence of a Grignard reagent, and it will produce MgX2 and PDR-R1 and finally the last step is the reductive elimination, and again with the cross-coupling product, and finally we will get the palladium 0 catalyst back, which can continue the catalytic cycle. So now we are going to study the mechanism of palladium catalyzed Kumada cross-coupling reaction. So according to the widely accepted mechanism, the palladium catalyzed Kumada coupling is understood to be analogous to palladium's role in other cross-coupling reactions. Very similar role that is playing in the previous reaction mechanism we have already seen. The proposed catalytic cycle involves both palladium 0 and palladium 2 oxidation state. Initially, the electron-rich palladium 0 catalyst 1 inserts into the RH bond of the organic halide, and this is the oxidative addition step. This oxidative addition forms an organopalladium 2 complex 2. Later is the transmetallization step, and the subsequent transmetallization with the Grignard reagent forms a hetero-organometallic complex 3. Before the next step, isomerization is necessary to bring the organic ligand next to each other into mutually cis position. Finally, the reductive elimination of 4 forms a carbon-carbon bond and release the cross-coupled product, while regenerating the palladium 0 catalyst 1, which can continue the catalytic cycle. For palladium catalyst, the frequently rate determining oxidative addition occurs more slowly than the nickel catalyst system. Now we will see the mechanism of nickel catalyzed Kumada cross-coupling reaction. The mechanism of nickel catalyzed Kumada cross-coupling reaction is quite different from the palladium catalyzed mechanism. The current understanding of the mechanism for the nickel catalyzed Kumada cross-coupling reaction is very much limited. Indeed, the reaction mechanism is believed to proceed differently under different reaction conditions when we are using different nickel ligands. In general, the mechanism can still be described as analogous to the palladium scheme as shown in this mechanistic pathway. Under certain reaction conditions, however, the mechanism fails to explain all the observation. Examination by Vicky and co-workers using tridentate terpyridine ligand identified intermediates of nickel 2 to nickel 1 to nickel 3 catalytic cycle, which involve 3 oxidation states of nickel, suggesting a more complicated scheme. Additionally, with the addition of butadiene, the reaction is believed to involve a nickel-4 intermediate. Therefore, this mechanism is quite complicated compared to the palladium one, where we can see in the palladium catalyzed mechanism we have only able to see the two oxidation state of palladium. One is palladium 0, another one is palladium 2. But here, depending on the ligand, when we use the torpiding ligand, the identified nickel intermediate belongs to the oxidation state 2, 1 and 3 during the catalytic cycle. But when we use also butadiene, the reaction believed to involve a nickel-4 intermediate also. So let us see the several examples of Kumada cross-coupling reaction. In the first example, we see that thiophene magnesium bromide is react with pyrrole with bromine substitution. So this is the pyrrole with bromine substitution is the aryl halide and react with the aryl magnesium halide to get this final product or cross-coupling product with carbon-carbon bond formation. In the next example, we have seen the pyridine with two bromine substitution react with benzopyrrole, magnesium bromide and thiophene magnesium bromide. And here we are getting this diaryl derivative. So this Kumada cross-coupling reaction is very important for the synthesis of different diaryl derivative with carbon-carbon bond formation between the reaction with a aryl halide with a aryl magnesium halide or aryl Grignard reagent. So now we will going to study the Suzuki cross-coupling reaction. Suzuki cross-coupling reaction is an organic coupling reaction wherein the coupling partners include a boronic acids and an organohalide palladium complex. Is used to catalyze this reaction. This reaction is named after the Nobel laureate Japanese chemist Akira Suzuki, who first published work on this work in 1979. This reaction is also called as the Suzuki-Miyaura reaction or the Suzuki coupling reaction. In the Suzuki coupling, the general scheme, the coupling between an organoboron reagent with an organohalide compound over palladium 0 catalyst and a base leads to the formation of a carbon-carbon single bond. Now we have seen the general reaction scheme here. This palladium catalyzed cross-coupling reaction between the organoborons with the organohalide or triplets in the presence of a base. The base is required because the transmetallation step is reluctant to occur without activating effect by a base. So the catalytic cycle is very much similar to that of the previously Kumada coupling reaction. The scheme shows above the first published Suzuki coupling, which is the palladium catalyzed cross coupling between the organoboronic acid and halides. The recent catalysis and method development have broadened the possible application enormously so that the scope of this Suzuki coupling reaction and the involved partners or involved reagent in the Suzuki coupling reaction is not restricted to aryl, but it also includes the alkyl, alkynes, potassium trifluoroborates and organoborates or boronate ester may also be used in the place of boronic acid. Some pseudohalides like triplet may also be used as a coupling partner in Suzuki coupling reaction. Let us see the mechanism of the Suzuki cross-coupling reaction. The Suzuki cross-coupling reaction mechanism is best viewed from the perspective of a palladium catalyzed coupling reaction. As we seen before, the catalytic cycle is initiated by the formation of an active palladium 0 catalytic species, which participate in the oxidative addition of palladium to the organic halide reagent to form the organopalladium intermediate with the oxidation state 2. The metathesis reaction with base gives a intermediate which via transmetallation with the boronate complex produced by the reaction of a boronic acid reagent with base forms an transient organopalladium species. Finally, in the reductive elimination steps leads to the formation of the desired coupling product and restores the original palladium catalyst with zero oxidation state, which completes the catalytic cycle. One basic difference between the Suzuki mechanism and that of the Stille coupling is that the boronic acid must be activated. For the example, here base is used for the activation of the boronic acid. This activation of the boron atom enhances the polarization of the organic ligand and facilitates the transmetallation step. If starting material are substituted with base labile group, for example ester, powdered potassium chloride affects the activation while leaving base labile group unaffected. Now let us consider the oxidative addition step of Suzuki coupling reaction. In most cases, the oxidative addition is the rate determining step of the catalytic cycle. So during this step, the palladium catalyst is oxidized from palladium 0 to palladium 2. The catalytically active palladium species A, as shown in the diagram, is coupled with the aryl halide substrate 1 to yield an organopalladium complex B. As seen in the diagram below, the oxidative addition step breaks the carbon-halogen bond, but the palladium is now bound with both the halogen X and as well as with the R1 group. The oxidative addition proceeds with the retention of stereochemistry with vinyl halides, while giving inversion of stereochemistry with allylic and benzylic halide. The oxidative addition initially formed the cis palladium complex, which rapidly isomerizes to the more stable trans complex. The oxidative addition we can see here after the formation of cis complex is readily isomerized into the trans complex. The oxidative addition is rate determining step as we discussed, and the relative reactivity decreases in the order of iodide greater than triplet, greater than bromide, greater than chloride. The oxidative addition involving the palladium 0 complexes is a SN2 type of mechanism based on the unambiguous evidence of stereochemical inversion of configuration at alkyl halides carbons. Therefore, if the alkyl halides, the alkyl group is optically active or having a specific stereochemical configuration, then after the Suzuki coupling reaction there will be a stereochemical inversion of configuration or at that particular carbon. The mechanistic studies have revealed that the apparently simple oxidative addition step consists of 4 concurrent isomerization pathways from cis isomer, which is initially formed to the more stable trans isomer. Now let us see the transmetallation step of Suzuki cross-coupling reaction. Basically, transmetallation is an organometallic reaction where ligands are transferred from one species to another. In the case of Suzuki cross-coupling reaction, the ligands are transferred from the organoboron species D to the palladium 2 complex C, but the base that was added to the prior of the reaction is exchanged with the R2 substituent on the organoboron species to give the new palladium 2 complex E. The exact mechanism of the transmetallation for the Suzuki cross-coupling reaction remains to be discovered. The organoborons compound do not undergo transmetallation in the absence of base, and it is therefore widely believed that the role of the base is to activate the organoboron compound as well as facilitate the formation of R1 palladium 2 tertiary butoxide intermediate C from the oxidative addition product R1 palladium 2 XB. Now the last step is the reductive elimination. The final step is the reductive elimination step, where the palladium 2 complex E eliminates the product 3 and regenerate the palladium 0 catalyst A. During deuterium labeling, Ridgetoe et al. Have shown that the reductive elimination proceeds with the retention of stereochemistry. Let us see the role of ligands in Suzuki cross-coupling reaction. The ligands play an important role in Suzuki cross-coupling reaction. Typically, the phosphine ligand attached to the palladium metal is used in the Suzuki cross-coupling reaction. The phosphine ligand increases the electron density at the metal center of the catalyst. Therefore, it helps in the oxidative addition steps. In addition, the bulkiness of the substitution of the phosphine ligand helps in the reductive elimination step also. However, the N-heterocyclic carbene or NHC ligand has recently been used in the cross-coupling reaction. Due to the instability of the phosphine ligand under Suzuki reaction condition, the heterocyclic carbene ligand are recently used in a variety of Suzuki cross-coupling reaction. The N-heterocyclic carbene are more electron rich and more bulkier than the phosphine ligand. Therefore, both the steric as well as the electronic factor of the N-heterocyclic carbene ligand helps to stabilize active palladium-0 catalyst. Let us see the role of solvent and base in Suzuki cross-coupling reaction. In the Suzuki cross-coupling reaction, which is different from the other coupling reaction in that it can be run in biphasic, organic water, water only, or without any solvent. The use of water as a solvent is also attractive because it belongs to the green chemistry as well as it is economic and provides the safety advantages. Frequently used solvent in Suzuki cross-coupling reaction mainly are toluene, tetrahydrofuran, dioxane and dimethyl formamide. The main role of the base in the Suzuki coupling reaction and which can provide in the reaction mechanism is to increase the reactivity of the boronic acid or activate the boronic acid towards the transmetallation. That is, the palladium halide complex converted it into a respective organoboronate. The most frequently used bases are potassium carbonate, potassium tertiary butoxide, cesium carbonate, sodium hydroxide, triethylamine, etc. The main advantages of the Suzuki coupling over the other similar type of coupling reaction include availability of common boronic acid, mild reaction condition and its less toxic nature. Boronic acid are less toxic and safer for the environment than organotin and organozinc compound. It is easy to remove the inorganic byproducts from the reaction mixture. Further, this reaction is preferable because it uses relatively cheap and easy prepared reagents. Being able to use water as a solvent makes the reaction more economical, eco-friendly and practical to use with a variety of water-soluble reagent. A wide variety of reagent can be used for the Suzuki coupling reaction, such as aryl vinyl boronic acid and aryl vinyl halides. Work has also extended the scope of the reaction to incorporate alkyl bromides. In addition to many different types of halide being possible for the Suzuki coupling reaction, the reaction also works with pseudo-halides such as triplet as a replacement of the halide. The relative reactivity of the coupling partner with the halide or pseudo-halide is iodide greater than triplet greater than bromide greater than chloride. Chloride has much less reactivity. Boronic ester and organo-trifluoroborate salts may be used instead of boronic acid. The catalyst can also be a palladium nanomaterial based catalyst with a novel organophosphine ligand. A catalyst loading down to 0.001 mole% has also been reported for Suzuki coupling reaction. These advances and the overall flexibility of the process have made the Suzuki coupling widely accepted for chemical synthesis. Suzuki reaction has both synthetic application as well as industrial application. The Suzuki coupling reaction has been frequently used in the synthesis of complex biologically important compound. The Suzuki coupling reaction has been used on a citronellal derivative for the synthesis of caparetrin, a natural product that is highly active against leukemia. Here is the synthesis of the caprotrin using Suzuki cross-coupling reaction. The Suzuki coupling reaction is scalable and cost-effective for the use in the synthesis of several intermediate for pharmaceutical or fine chemicals. The Suzuki reaction was once limited by high levels of catalyst and the limited availability of boronic acid. Replacement for halides were also found, increasing the number of coupling partner for the halide or pseudohalide like triplet as well. Scaled up reactions have been carried out in the synthesis of a number of important biological compounds such as Cl1034 as shown in the scheme, which is used as a triplet and boronic acid coupling partner, which was run on an 80 kg scale with a 95% yield for the industrial production. Suzuki cross-coupling reactions have both synthetic as well as industrial application. The Suzuki coupling reaction has been frequently used in the synthesis of biologically complex compounds.